Hello, this is Module 3. Module 1 introduced the OSI model, so how the whole communication happens within Ethernet. And Module 2, if you recall, it was cabling, wiring, DMARC, horizontal wiring, vertical wiring, and the cable itself. So that was more like a layer 1. So this module, it will introduce the higher topics. So here you'll see how MAC addresses work. I've been mentioned MAC addresses many times. They work on layer 2 with the switches. We'll get into the layer 3 with the IP addresses, some of the mask, the gateways and things like that. And also there's some ports that you work with, your DNS, and some troubleshooting tools. So the MAC address, or the media access control address, is a 48-bit identifier for your network card, for your interface, the physical interface of the computer. The MAC address is embedded on the card, is a unique identifier, and you should have only one of those in the world. It's a unique number. There are plenty of numbers there, and hardware is being recycled many times, so numbers can be reused. But those are the ones that you need in order to get into the higher layers to get an IP address. Okay, the MAC address is broken up into two pieces, and we'll get more into that, but it will show you what the manufacturer is, the first half, the first 24 bits. It's the identifier for the manufacturer of the card, and the second half is for the your identifier. We'll also get into IPv4, which is a 32-bit address, IPv6, which is a 128-bit address, some of the transport layer, layer 4, and some of the DNS for the fully qualified domain names or FQDNs. So like I said, the MAC address is broken up in two pieces, two halves. The first half is the OUI, the organizationally unique identifier. That identifies who is the manufacturer of that card. Is it Broadcom? Is it Intel? Is it Epson? Apple? Any of those manufacturer will be identified with those first 24 bits, and those are assigned by the IEEE. And the last 24 is an extension or the device ID. That's unique for your device for that manufacturer. So that gives a lot of flexibility for them to use those 24 bits for, to have a lot of devices, the physical devices assigned. Now, the switch, like I said, the switches works at layer 2. So they use the MAC address to identify devices. Switches are not aware layer 3. So switches don't know where your IP address is. They don't know anybody's IP address. All they know is how to forward traffic, how to switch traffic at the layer 2 level with MAC addresses. So when any device connects to the network, any device connected on a wire, and that link comes up, when that link comes up, that you're going above layer 1 to layer 2, the sender or the client or whatever device you're connected to the network would identify itself with a switch. So you see it's the stored MAC address, and this one says 1234.56.78 ABCD. And then it will forward that to the switch and said, hey, I'm this device and I'm connected to you. And the switch will register that. It goes, okay, you're coming in with me on port 5. So I'm going to put on my MAC address table. And now I know that this MAC address is on port number 5. So next time I see traffic that's destined to you as a receiver, then I'm going to look for that MAC address, see what port you're on, and send it to you. If you move to another switch, let's say you disconnect your computer, go to another switch, then there's an aging time on that switch that will tear down that registration, and you disappear from that switch, and then you reappear on the new switch where that switch says, hey, I have a new client here that's coming in with this MAC address, and I have it on port 15 per se. And it will keep track of that device. So now that you register with that, the next thing that your computer would do, or any client would do, your laptop or your phone or any tablet, it's to say, hey, I need an IP address. The only way to talk on the internet, it's on any network for that matter, even a small LAN or a local LAN, is through IP addresses. So the computer goes and says, I need to have an IP address. Now, the IP address can be manually configured by the administrator, but let's say at Miami-Dade, we have active during the day 18,000 clients. So you're not going to keep track of all those 18,000 and assign it an IP address manually on every device. So you go to a server that's called a DHCP server, Dynamic Host Control Protocol. And the DHCP, which we'll look later, it's the one that actually hands out and keeps track of those IP addresses. So this is a device that especially it just built, programmed, and made for to do that, to do an address management, to hand out all those IPs and keep track of those IPs. But we'll get more into the HCP on another chapter. So when you get those IP addresses, the two options. You can get an IPv4, IP version 4, which is a 32-bit IP address, or IPv6, which is 128 bits. And you see that at one point a few years ago, I would say like 10 years ago, they were afraid that we were running out of 32-bit IP addresses because it's a limited number, of course. So they came up, the IEEE came up with the IPv6, which they quadrupled that and they went 128 bits, right? So by doing that, they said this way, it doesn't matter how many devices you have on the internet, you will never run out of IP addresses because now you got a zillion IP addresses with IPv6. It's implemented a lot in Europe, not so much in the United States, although some companies like T-Mobile uses IPv6, but we'll describe each one of them individually. So first is the IPv4. IP version 4 is a 32-bit IP address, like I said, and is written on a decimal format. So you see the example here of 72.56.105.12. So each number, it's defined as an octet. It's 8 bits. Remember, it's 32 bits. So it's each octet is 8 bits. So 8 times 4 is 32. So you have your 8 plus 8 plus 8 plus 8. Now, when you have 8 bits, we have to go a little bit into binary to get into that. But 8 bits will give you a number between 0 and 255. So on an IP address, IPv4 IP address, the lowest number will be 0.0.0.0, and the highest number will be 255.255.255.255. There is no way possibly to have a number that on any of those octets that is higher than 255. You can never have 300.400.750.600. Never. It's like I said, the maximum is 255.255.255.255. There is a classful addressing to kind of like group addresses together, and they're separated by classes. So they have the class A, class B, class C, class D, and class E, and we will go to each one of them individually, and you'll see where the classes are. But it's just a way to separate the range of IP addresses that you can get on every block of IPs. Now, all of these IP addresses are licensed, and you have to basically apply to get a block of IP addresses assigned to your corporation or your enterprise or your network. Unless you're a large enterprise, you will not get IP addresses. The public IP addresses, those the ones that hand down. Miami-Dade owns the public IP space of 147.70.0.0. And it goes all the way to 147.70.255.255. So everything in the middle there is assigned to Miami-Dade, and other businesses do that. You can have larger blocks, you can have smaller blocks, it's all kinds of different things. So those are the public IP addresses. But the IANA, which is the organization that controls the IP addresses, have already said some IPs that are for private use. Private use is something you can use inside your network that don't need to get out to the internet. There are ways for them to do it, but it's something that you keep those addresses inside and they can be used by anyone. So most of you, if you have a Comcast or AT&T router at home, most likely your IP addresses inside your home are 192.168. That's something. And that's because it's using private IP addresses. That's the most commonly used, the 192.168. And if you see here, it goes from 00 all the way to 55. There's another range that is from 172.16 through 172.31. And the other range is the 10.0.00. Anything that starts with a 10, because now it goes from 000 through 10.255.255, meaning that anything that starts with a 10 can be used as a private IP address. We are using a 10 something IP addresses inside the college network. for management, for things that we just need to assign an IP address, doesn't need to go out to on the internet. We can assign one of those 10 IP addresses, and this way you have thousands of IPs that you can use. Okay. Now you can have also the classless addressing. The classless addressing is where you kind of like break things in the middle on the ranges. We'll get into that. So to assign your IP addresses. And you have what's called the CIDR. This is pronounced CIDR, CIDR, which is a classless interdomain routing notation, which is the one that what you do, you use a slash to find which is the number of bits that belongs to your network and which portion of your bits belongs to your workstations. Now, those private IP addresses, the 10.0.0.0, the 172.16, and the 192.168, those are private. They can be used internal into your network, and they cannot be seen from the outside. On the outside, you have to be on a public IP address in order to be able to have communication across. So to overcome that, the IEEE had assigned one of the protocols that's called NAT, N-A-T, Network Address Translation. So it's a technique where you have one public IP address and then all the other private IP address are masked behind that one IP address. That's what it's called natting. And the industry, they just call it people, you're doing natting. You're doing NAT, you're actually natting. So at your home, when you connect your Comcast or AT&T router, you will get one public IP address that actually belongs to AT&T or Comcast, and they assign it to your location. So now you got one public IP address, and then you can have all of these private inside the 192.168, and everything get translated to that single IP address. And that technique would actually track communication if you have multiple computers on the inside. Even if you have 100 computers, you can still communicate all of those 100 and be basically impersonated by just one single IP address. You can also have the port address translation, which is another process that is assigning a TCP port to each session. So you can keep track by the TCP port that you're using. The NAT has two variations, which is called the SNAT or DNAT. SNAT is the source network address translation, and DNAT is dynamic, right? So on the source NAT, the gateway assigns the same public IP address to a host each time it makes a connection to the internet. And in the dynamic, the gateway makes like a pool of addresses that is assigned to multiple hosts inside. There's a graphic coming up, and I'll explain this better. Okay, so now will make more sense. So you have a public IP address assigned by your provider, right? And on your gateway at home, you have the 92.52.44.1. On the inside, you have all these computers that are 10.1, 120, 10.1, 121, 10.1.1.122, 10.1.1.123. So with with port address translation, what it will do is that it will assign one port number, one TCP port number to each workstation. So the first one will use port 8000, second one 8001, 8002, 8003, and so on. And that's how it identifies all that traffic. So let's say computer .120 requests a web page from Google, but .121 requests a page from CNN. So when it goes out to the internet and get those to those web servers, and you get a reply back, then that gateway, your router there, it will keep track and see who's the one that requested Google and said, oh, that was the client with 8000. So let me send it back to that one machine, which it was actually, 10.1.1.20. He requested that through port 80, and it comes back up on that one to that specific machine. And then when it comes with reply from CNN, it goes back to the router, and the router goes, okay, so this one belongs to the 10.1.1.121. So it keeps track of that. It's a lot of I'm not going to say a database, but it's a table that keeps a table of that the path table. Now IPv6 It's a different animal. IPv4, it's four sets of numbers, and those are decimal, right, from 0 to 255. So on IPv6, if you do decimal, that would have been a huge, big number. So what they opt out to do was to represent those IP addresses with hexadecimal. I posted a video that talks about binary and how do we deal with binaries. So I encourage you to go and see that video on addressing on binary. So I think I touch a little bit on the hexadecimal too on how this works. But this is hex. So the numbers are digit each digit location goes from 1 through 16. So that's why you see the 9C58, 00CC, and so on. But each block is 16 bits. You see, remember how on IPv4, a three-digit number, 0 to 255, represent 8 bits. But on this one, you got 16 bits represented, but only 4 positions, right? So it makes the address a little smaller. So also, when you see that you have a string of zeros and they're sequential zeros, they can be replaced with 2 columns. Is a way to minimize numbers and not repeat the numbers like that, make it easier to read, and also the routers themselves would do that, so I can eliminate that. So if you see that example on the top, you'll see that that can be compressed as the example on the first one, right? But that eliminates only one block of zeros, but there's 2 blocks of zeros that are sequential. So you can actually do that like in the second line, that's the preferred method to say, okay, why am I going to compress, represent with the double column a one set of zeros, we can actually eliminate 2 sets of zeros. So when you see that, that's what it actually means. It's only done for zeros, nothing else, but just a way to represent the IPv6 address in a more condensed format. Now, this is some of the terminology that you'll use on IPv6. It's a little different from IPv4, but a link is something, any LAN bounded by routers. Any LAN bounded by routers, it'll be called a link. Neighbors, of course, kind of like on IPv4, it's when you have 2 or more nodes on the same link. So in IPv4, that's called more like a LAN, when you become on the same LAN. But in IPv6, you actually say that you're neighbors. This is also dual stack is something that is used a lot. Computers, even your phones, most of the, I would say all of the phones that supports IPv6 would also support IPv4, of course, because it's an older protocol. So it will support both. And it's capable of using both IP address formats. It will get an IPv4 and get an IPv6. When you have that, that's what you call a dual stack. If you get into troubleshooting and they ask you hey, it's your computer dual stack, that what they mean is that are you using IPv4 and IPv6 at the same time? Because you can, even though your network doesn't support it, IPv6 will still be enabled and grab like a local IP address to put himself into an IPv6 network. Tunneling is a method that you can use in case there's somewhere between your path to your connection over your network that doesn't support IPv6, so you can actually encapsulate IPv6 over IPv4 and get to the other side. So that's what IPv6 calls tunneling. And on IPv6, the interface ID is the last 64 bits of your address. Kind of like the MAC address. The MAC address, the first half is your manufacturer, your identifier, your OUI, and the second half identifies your workstation. On IPv6 is the same thing. The first half identifies the network, and the second half of the 128 bits, in this case 2064, identifies your interface or your workstation, your machine itself. That's a number that's unique to you. Sometimes it actually puts in the MAC address, or it makes an algorithm to come up with a random number based on your MAC address. But that will make that number unique for your IP address. On IPv4, IP is assigned. So at work, at the workstation in Kendall at the campus, I will get 147.70.40.57. So that's unique to me. That 40.57 is unique to me. So what IPv6 does, it comes up with a random number based on my MAC address, which is a unique number, and come up with a unique interface ID that identify me, and then I'll have no conflicts with anybody else having the same exact IPv6 IP address. So it's a very clever way to just guarantee that there's no duplicates on the network. So on IPv6, you can have different types of IP addresses. You can have a unicast address, which is a single node. This is your computer. And then you have a global address, which that can be routed on the internet, right? A global address is similar to a public IP address, something that can go out on the internet. If you have something similar to the private, remember the 192.168 that you can use inside your network? Well, in IPv6, it's called a link local address. That's something that you can communicate with nodes on your same link. The link, remember, link is the um, equivalent to a LAN on IPv4. So when you have multiple machines using the same link or like the same area, then they can have a link local IP address, and that definitely you can use NATing at the edge if you have to, but that's what is called in IPv6. You can have a loopback address. This is the same on both IPv4 and IPv6 that is used for testing on an interface. A loopback means a way that you kind of see yourself back on the network. If you want to test your connection, it's kind of like a trying to talk and hear yourself. It says, oh yes, I'm talking because I can hear myself. That's a loopback. That's I say something, I send some traffic, and then I get it back again. I was like, oh, there you go. I'm talking. If I can hear myself, somebody else can hear me, right? So that's what the loopback addresses are. It's just another IP address that, in addition to your workstation IP address, that the system will use to talk to yourself. A multicast address, like the name says, is to multicast, is casting to multiple sites. So that's to deliver to all nodes on the network. And then also you have the anycast, which is to multiple destinations that are close to you. You know, it does a multicast sends to like everybody everywhere that it can reach, but anycast is only is similar to multicast, but multiple destinations that are only close to you. If they're too far from you, like the connection is, remember how the ping, you can tell from the ping how far is the connection to come back to you. So if it's kind of like too far, you said, now, I'm not going to anycast to that workstation because it's too far for me. I'll let somebody else handle that one. So here you see how the global address on IPv6 will start with 001, and then you have 45 bits with the global routing prefix, just like it's a number that was assigned to your global routing. You still have like a subnet ID and an interface ID. Remember that the interface ID is always 64 bits, is half for your 128-bit address on IPv6. So you still have that, but on the first 64, they are broken up in the 3 bits for to identify there's a global address, 45 bits following that with the routing prefix, and 16 bits for the subnet ID. On the link local, the first 64 bits is actually always, if you see this says FE80, FE80, and in this case, it has colon because there's a whole bunch of zeros in the middle. So the first 64 bits always will start with FE80. If you see those binaries, the 1111 space 1110, that's E, and 1000, it's 8, and then 000 is 0. So that will become FE80. So we always have that on your first 64 bits on your workstation, of course, the second half. For the loopback address, it will be a string of zeros. That you see it's all 00, 128 bits, and then 1 bit at the end to identify that that's your loopback address. So here, if you do an IP config on your computer and you are dual stack, you will see like on the left-hand side that it has a link local IP address of FE80. There's a colon, and I cannot read those numbers. But anyway, it will start with the FE80. And then you have an IPv4, so it means that this is dual stack again. It has both of them. And this is a 192.168.56.1. That IP address is also the IPv4, and it's a private IP address. On the right-hand side, I put the one from my home computer. I have my internal networks called Kinobit internal. And you'll see that my computer has the FE80 also is showing as a link local IP address. And for my IPv4 is at 10.10.100.32, which is the a private IP address that I'm using inside my home network. Okay, so you will see that you know what please remember that the FE80, once you see that, that's a link local. That's more like a private IP address on the IPv6 world. Okay, so what happens when you connect a machine on an IPv6 network? The machine will do what is called a SLAC, a stateless address auto configuration. It doesn't require a DHCP server. It will do an auto configuration. So the first thing it does, it will take that FE80 or FE80 address and create that first half of the 64 bits, you know, for your prefix. And then on the last 64, it will generate a number based on your MAC address, right? This is a number that is an algorithm there that will take your MAC address, the 48 bits. Remember, 48 bits is the your MAC address. It will take those 48 bits and then make a hash, an algorithm to come up with those 64 bits and generate a number. Then on the step two, it will go into the network and make sure that it's a unique address, that nobody else has that IP address by chance. If it is, it will keep it. If it's unique, it will stay like that. If it's not, and somebody else, well, probably another machine that was probably from the same manufacturer, it is possible that the algorithm generates the same second half of the 64 bits. So it will back off, just rehash that again. Remember, a hash is just an algorithm. So rehash that again and come up with another number and then go again. It goes, okay, am I unique on the network? And once it's unique on the network, it's allowed to join. Once it joins the network, then it will ask the router, if there's a router, that can provide a routing information. So that's the your RS, your routing solicitation message. They will come out and say, hey, when I need to get to route out of my network, or out of my link, where do I go? What do I do? So that's kind of like on IPv4 when you assign the gateway. Remember, the gateway is kind of like that door to get out of any LAN, or like if you're in a room, if you want to get out of that room, you have to go through the front door. So that gateway is actually given by the router when you receive that router solicitation message from an IPv6. But on an IPv4 world, you get that from the HCP and it's all handed out to you. But on IPv6, a lot of it is an auto configuration. It does it automatically and it doesn't require any controls over that. It says, okay, let me get that. And if the router provides me the information, that means that I have a way to route out of my link. If I don't get that information, it says, okay, so I'm self-contained, is a closed link. That link is, or the LAN in that case, is just a group of computers together, and we don't go out to the internet. We don't go anywhere else to any other machines because there's no router information. So it will just stay like that. All right, so that was up to layer 3, right? Layer 3 is where your IPv4 and IPv6 IP addresses are assigned. And then the next layer is your transport layer, right? So here we're talking about ports and sockets. I mentioned before that ports is more like a channel, right? If you want to watch sports, you tune to that channel. If you want to watch news, you tune to that channel, and you can only watch news on that one channel, and you only watch sports on that other channel. If you go to the sports channel waiting for the news, you'll never going to get it unless there's sports news, right? So that's why you have to there's a ports assigned to certain processes in the networking. I mentioned before, and there's a page there on the Blackboard that talks about the well-known ports. That's from 0 to 1023. Those well-known already assigned ports, and also they are registered ports, which not all of them are registered. Some of them are still kind of like up in the air, not fully assigned to something. That is 124 to 49,151. And then from that point on, it's all dynamic and private ports. So most of the games and most of the programs you'll see using ports higher than 49,000, 55,000, on the 60,000, you see all those ports there. Most of the Trojans and viruses and malware comes on those high ports since they're not assigned and the computer doesn't really know where they are, or systems don't know where they're really assigned to. So that's how they can get into your system. But on the well-known ports, you have that value of the port that you want to communicate with. So on IP representation, you'll do the IP address, colon, and the port number that you want to talk. So that means that the communication that I'm doing is going to be on to 1043.3.87. That's my destination, and I want to talk to that destination on port 23, which in this case 23 it's telnet. So it's already pre-assigned for that. Okay, and this is slides a little backwards because the client will set the request, which is the line at the bottom, not the line on top. Usually you read from top to bottom, right? On this one, you need to read it from bottom to top. The client will do a request for telnet connection on port 23 to the server. If the server has port 23 open and is listening for telnet traffic, he will reply back with the acknowledgement for the connection of port 23. It says, yes, my port is open and I can get the connection. Please, let's just start talking. So he makes the request and then he comes back. The same way, if you have a web page and you want to communicate web pages, it's HTTP is port 80. So you make a request on port 80. If the port 80 is working on this, is open on the server and is listening on 80, then it will reply back, says, okay, I acknowledge that you want to set up a connection on 80, so we can start communicating web pages, right? Now, if I go to the server over port 80 and this server doesn't have 80 open, the only open that is in this case will be 23, the request is denied. He said, I don't know what you're talking about. I don't have any port open on 80. Since I'm not listening, the server is not listening on those ports, so your request is just ignored. I can go to an IP address, and let's say this one is a server that has a telnet connection. I try to open HTTP, HTTPS, SSH, any connection, and since the ports are not listening, my request is ignored. I'll never get an answer. So you'll get an answer only from that. So this is me trying to tune on CNN. I said, hey, tell me what's the cartoons for today, or show me the cartoons for today. And CNN goes, I'm not showing cartoons, so I'm going to ignore your request, right? So that's pretty much how this works. All right, so all these port requests, of course, is your software that knows that. You don't have to specifically tell your computer, I want to make a connection, and it has to be telnet or now with DNS or anything like that, because if you're doing a specific request, the computer is already programmed to do that. So domain names and DNS. Remember that computers, they talk through numbers. They don't know about names, right? The networks, the routing doesn't know about any names. So you need to have what is called a URL, a uniform resource locator. A URL is just like an address identifier that binds you with the fully qualified domain name. Is a domain name that is assigned to your location, www.mdc.edu. It's something that we're using, and it gets assigned to us. Now, for the fully qualified domain names, you have to reach the top level domains. The top level domains is where all the information are, where to find the different websites. When I say the websites, I mean, like in this example, you got the .arpa, the .mil, .edu, .gov, .com, anything else. That is a set protocol that it's just meant to do that translation. So on the DNS name, you have the namespace. The namespace is your entire collection of names that you have. Jobs.mbc.edu, the phone book.mbc.edu. All those namespaces that we have, it's that collection, all those DNS names that belongs to us, right? But each DNS server is handled by your local enterprise. And we'll get into that in a second to explain that a little better. So your name server is the one that holds all those databases, and they're all organized in a hierarchical structure from top to bottom to see where your databases are. Now, the resolver is the client. When you're trying to get a request from a DNS server, you are the resolver trying to get a resolution from a fully qualified name to an IP address. Fully qualified name meaning www.google.com, www.mdc.edu. Those are fully qualified domain names. So on my namespaces, if I'm an organization that I have my own DNS names, right? I have to have what's called a authoritative name server, right? That's the authority with all the names and IP addresses for my domains. So that's the one that says, okay, jobs.mdc.edu is this IP address, phonebook.mdc.edu is this IP address, and so on and so on and so on. So you can organize that with DNS zones. You got multiple DNS zones, and you can organize that through different zones. But my authoritative name server, which we have here at the college, a set of servers, they're the ones that hold all the those domain names that we have in our namespace. In class, I can show you the access. I have access to our DNS server, and I can show you the collection, the incredible names that we accumulated through the years, and they're still in use. So when you have your name servers, like I said, Miami-Dade has its own set. I said there were two. So we have a primary DNS server that's the one that holds all the information for my organization. A secondary, which is a backup. The way we have it at the college is actually it's on a. We don't have primary, secondary. We have an active, but you have to point to one of them primary and point to the other one as a secondary. But somebody else can point to my second one as to be a primary and the other one as a secondary, vice versa. We can do it either way because they're both an active. You can have also a caching DNS server. That's the one that actually caches information, it stores the information. So if you need it, you don't have to do the request again. It's kind of like if I ask for a phone number, and I asked for so many times that the person in the middle said, let me write it down. So next time I don't have to open the catalog and look for that name because too many people keep asking for that same number again. So I'll just keep it here handy so I can hand it out quicker. So that's what a caching DNS server does. And then you got a forwarding DNS server, which what it will do queries to other servers. It's just kind of like it's like a man in the middle. He's the one that the server will get that request, and he doesn't have the information, but he can get that information for you. So that's the forwarding DNS server. And you can have any of those on the same server at the same time. So you can have your primary DNS server also working as a caching DNS server, because the primary DNS server is the one that will get requests for anything, not just for your own organization, but also for other services outside. So you need to contact other DNS servers. Like I said before, the DNS is a hierarchical structure, and we'll show you that. On the top level, which they call the top level domains, is called the root. Those are the ones on top. And let me show you the next slide with the structure. So right on top, you have what's called your DNS root servers. And your DNS root servers sit on top, and those are the ones that have the information about the top level domains. The top level domains is the .coms, the .org, the .edu. Now there's tons of those more top level domains. It's just not .com.org and .edu. There are many more, and each country also can have their own. I think Germany is .de. I think Colombia is .co, and like that. I think Mexico is .mx. So you have all those top level domains, and those top level domains are the ones that know where the authority servers are. Remember, the authority server is the one that resides on my organization. Since I am Miami-Dade, I have an authority server with all the domain names and all the servers, the fully qualified domain names that I have in Miami-Dade. Nobody else knows that. So when someone needs to come to Miami-Dade and say, hey, what's the IP address for that server that was named phone.mdc.edu, So it will go to the root servers, and it goes, oh, you're looking for an EDU. Go ask the EDUs. Those are the top level domains. So the top level domains comes and says, oh yes, there is an mdc.edu, and let me forward you to that server because he's the only one that can give you that information about mdc.edu domains, uh, qualified domain, fully qualified domain names. Uh, if you ask for, I don't know, to get an IP address for FIU. Well, Miami-Dade servers doesn't know anything about FIU, what service they have, and I don't care less what they have or what or any other EDU has. So, of course, I will not have that information. So the top level domains, when it says, oh, you're looking for an IP address for FIU, FIU.edu, so let me send you to the authority server at FIU, and they're the ones that will provide the translation for you. Now, this translation happens so quick. Your computer will go request that, and the reply comes back within milliseconds. So anybody that wants to reach anything inside Miami-Dade, it has to come to the authority servers at MDC in order to get a reply back. So, and that's how it goes. If it's not there, of course, you won't get a response because we don't. You're asking for the Kenobi MDC.edu. It doesn't exist. It exists internally, which we'll talk about that. There's an internal DNS and external DNS. So, but to present it to the external one, it's not there. So it will not get a reply. I said, I don't know. They will get no response at all. Okay, so let's see the mechanisms on this. So you are the client computer, and I said I'm at home, right? And I have my Comcast connection. And if I go on my computer and do ipconfig /spaces/all, it will show me who's my DNS servers, and most likely it will be my Comcast router, 192.168.1.1, something like that, the gateway, and he will do more of a relay to ask the Comcast DNS servers, or you may have your Comcast routers configured, DNS servers configured on your router, and it will point to that. That will be your local DNS name resolver. So on the step number one, I go to my local DNS server, like I said, in this case, my AT&T DNS service or my Comcast DNS service. I said, hey, how do I get to, I need the address for the mdc.edu. So it goes to the root service, and then he replies back. He goes, oh, go ask the top level domains. So on the top level domains, he goes, I'm looking for, the name servers for this mdc.edu. He will reply back on number 5 and saying, okay, you need to go to this top authority server that is called mdc.edu. So on number 6, you go there. I said, hey, so what's the IP address for www.mdc.edu? You get the reply to your local DNS servers, the resolver, and that will relay the information back to your computer. So your computer now has the real IP address for www.mdc.edu, no longer a name. Now you have an IP address. Now, guys, for every communication you do on your computer, you have to do a DNS resolution, because unless you know exactly the IP address that you go into, which nobody does, unless it's something very, very specific, you have to go with a name, a fully qualified domain name. If you go into www.cnn.com, CNN, I don't know where the IP addresses are. They might have multiple IP addresses. It depends if I'm on the East Coast and the North and the South, the West Coast, the North, the South, Central, wherever you are. You might have local CNN servers that you want to go to. You don't want to go, to one that is too far from you, because it's the same content anyway. So my computer has to go a DNS resolution first, port 53, and said, hey, what's the IP address that I should contact for CNN.com? And it goes all through this process to the top level domains to query, okay, it's a .com and you're looking for CNN.com, so let me forward you to that authority server, and he will give you the IP address, and then my computer will get that IP address and communicate at that layer 3, because the layer 3 is the only way to communicate across networks, across multiple routers. It's IP address to IP address. Layer 2 on the MAC address, that's only for you local. If you're local for yourself, yeah, at the local level, they can talk to MAC, It's on the MAC address level. But if you want to route somewhere outside your network and through multiple networks, you need to go through, through an IP address layer 3. And the only way to get there is to request on a layer 4, port 53, a DNS resolution. Once you get the DNS resolution and you get an IP address, now your computer can do something. Any communication will have to do that. So this communication is complex, but it can get more complex. If your caching server, if you have a caching server, and it's not your authority server. Remember, authority server is a server in your location, in your enterprise. Um, um, the caching server might have only information on your local clients. Now, your name servers, your servers in your organization needs to have access to the root servers. Remember, the first thing that you do is to go to the top, right? Now the top level domains. You go to the top to the root services, and the root service is the one that will send you down to .edu, .com, .org, and all the top level domains. Well, your name servers have to be pointing to some root service. If they're not pointing to that, or they are not having a good communication, your whole process will break. Okay. Also, if your top level domains is aware of some intermediate server rather than your servers, it could break because that authority server that you have on your premises, the one that belongs to Miami-Dade, I update something, and if the intermediate name server doesn't update immediately, then that information is lost. I just created a new server, and I'm going to call it, the CT-1134.mbc.edu, and I published that on my authority web service, and it's already there. But it has to propagate. It has to propagate to there's an intermediate server. It has to propagate to that one, because the top level domain might be pointing to that intermediate and not directly to my server. So that might break there. So sometimes when you publish new DNS names, you gotta give it a few minutes to propagate on the internet, because if there are any intermediate name servers or any caching servers, then you have to wait until that propagates or they're aware of it. Okay. Now, when you do a DNS request, there are two types: recursive lookup, which recursive, it demands a resolution. Either you tell me, and if you cannot find it, then let me know. And then there's the iterative, that it will make the query to other servers, and they'll get the information if they have it, but it doesn't demand a resolution. It says, I'm trying to look for this, but if I don't, then it's okay. But most likely what you want is a recursive lookup, because a recursive lookup is the one you get an answer, you want to get to that whatever site you want to go to, right? Now, you want to complicate DNS? Here it is. DNS is not just a source of fully qualified domain names to IP address translation, right? It has a lot of records. You can have the name to address is what's called an A record. An A record is what makes a name to an address mapping to a host. Now, if you're using IPv6, it's called a quad A. The AAAA is called quad A. That's a name to address, but if you're using IPv6, then you can have a CNAME, which CNAME is more like an alias. It's an alias, which is an alternative name for a host. So I can have actually, we do have a CNAME that's called zoom.mdc.edu. So if you want to access the Zoom servers with the Miami-Dade accounts, that actually doesn't sit in Miami-Dade, and it doesn't really have a mdc.edu address, but I created one, and that alias internally, I point to the address that it's supposed to go to. I can make the resolution, even though you're asking for something that is not valid, but I'm making it valid. Now I'm creating an alias. It's okay, I'm going to create a CNAME that it says, whenever you come to me and ask me, hey, what's zoom.mdc.edu, rather than give you one of my IP addresses for my service in my institution, I'm going to give you somebody else's, and that's where this thing is being hosted at the Zoom server somewhere in the United States, somewhere in the country. It's hosted there, so I'm going to give you to that IP address. I'm going to point you there. I'm being I'm being sneaky, and I'm going to relate that to you. But then I give you, by doing that, I get the convenience to having a very easy to remember name, zoom.mdc.edu. Because the other one was like, I can't remember what's the actual name, but it's a very complicated, and at the end it's like zoom.us. So you're not going to tell the professors and the whole faculty said, hey, when you go to Zoom, oh, don't do MDC.edu, has to do this. It's not easy to remember. So we created that one. Also, you have a PTR, which is a pointer. That's for use for reverse lookups. That if I have a name to an IP, I can do that. That will do a reverse lookup. So I said, okay, I know that www.mbc.edu is 147.70.29.80. But if I do a reverse lookup and I said, okay, what's the name for 147.70.29.80? And it will provide services that, oh, you give me an IP that belongs to me and what name I have to that, or let me look at my table. Like, oh, here it is the matching name. I'll give you that. Um, then the NS record, NS record is just your authoritative service. Where am I pointing for authoritative service? MX records is for mail exchange records. That's to point to your mail service. So when you go to mail.mbc.edu, you actually go into your mail service that they know that this is used for email traffic. And also you have other ones as a service record. The service record is for more um, other specific services. It's sometimes even for to request a some specific numbers that you need to have or need to send to your receiver. You can put it there. Many times the service records are used to verify that you own your mdc.edu. Let's say someone wants to point to me and he says, yeah, but I want to make sure that you own mdc.edu. If you do, go and add a service record and put this string of numbers. So I'm going to try to read it back from that service number, and if I get it, it means that you do have access and you're capable of adding service records. And if you do, then I can trust you because hey, you have the power to do that. You were able to do it when I requested it. So or to, like I said, to verify that yes, you are who you are, so the companies can start exchanging information. And text record is just text. It's holds it's a free form text. Whatever you send me, I can put it there. Like I say, it's sort of like a service record, but this is a text record. And the text record, it just to me to put some information there for others to retrieve if it's required to. For the most part, all you want is your A records, maybe your PTR records, your quad A's if you have IPv6, your NS record, of course, to see who's your authoritative server. So how do I get this service to work? Well, there's a service. It's a software. Bind is one of the most popular ones. It has been around for so long. Bind it was made at their Berkeley University in California, I think it is. So it's called the Berkeley Internet Name Domain. And it's the most popular software, and that became an open source. Remember, open source is that software that is released to the public and available to anybody to use it. Microsoft has a DNS service that is built in on their any of those servers. You can use that as a DNS server. You know, it's also valid. But Bind is the one that Bind runs mostly on Linux. So Linux is a little bit more stable. So one of the preferred ways to set up a DNS server is through Bind and Linux. So Windows server, well, not Windows server, but any server can do what's called a split brain or a split horizon, where you can handle internal clients and external clients differently. External clients are people coming all the way from the outside to your organization, right? Any of you from home trying to reach any DNS resolution at Miami-Dade, it will be considered as external client. But for anybody internal, I can have another server that knows everything about the outside, but also there are some unique names that they're only propagated on inside your organization. So those for internal clients and for internal resolution. My server, the kenobi.mdc.edu, is only internal. It doesn't get propagated to the outside because that server is not is not doesn't have access to the internet, so it cannot be seen from the outside. But from anywhere on campus, you can go to, you know, HTTPS kenobi.mdc.edu, and you'll get the page. Well, not all the time. I have it restricted to certain subnets, so it's not from everywhere. But that's done on the software individually. But what I'm saying is that there's some names that you can, if you can create your own names for printers, for some devices, projectors, anything like that. So you can create those names that don't have to be published to your authority servers facing the outside. There's a whole collection of names that it gets only on the internal. So that's what it's called the when you have the split horizon deployment. All right, so now we're shifting away from DNS, and this is more into troubleshooting. So on Windows, you always have the event viewer. The event viewer provides a whole overview or anything happening on Windows. So you can have your Windows logs, on your custom views. You can have all the logs that Windows generates, and that you can see it, and it will give you some idea of what's happening. But any logins, a failure or things like that, it will be on your event viewer, and you can troubleshoot problems from there. So the last part of this chapter, it's all based on troubleshooting. We have seen some of this in class already. Ping is a good utility for Windows, and also Linux uses the same. If you have a Mac, you can also go to a terminal and use Ping. PING is a packet internet grouper, and that's a small utility that it will send a packet, and it requests what's called an echo request. It would ask for a response, and it will give you a number that represents how many milliseconds took that request to go out and come back in. So it is installed on most systems. It's available on any Windows, like I said, on any Mac computers or any Linux machine. It's bound to the NIC card, or any NIC card that is on a computer can use Ping. It is already configured. It communicates with the network. So that's a way to also troubleshoot any communication. If I get an IP address, or I have a manually assigned IP address, I can ping something else on my same LAN, on my same network, on my gateway, just to see if I'm reaching outside. See if can I see each other? Can I see my computer next to me? Can I see the computer on the gateway or anything like that? So the ping protocol uses ICMP, which is the Internet Control Message Protocol. That's the ICMP is a protocol that ping uses, and the type of traffic is an echo request, or the echo protocol, and that uses TCP or UDP. Okay, you see the one port 7. TCP most for send a traffic and request a reply back. Remember that TCP does, but on the reply, all I need to send you is a reply back, so that's a UDP. If you send me a ping and I reply back to you, do I expect you to tell me that you received my reply? No. So the initiator sends a TCP request over ICMP with an echo request. I said, hey, I'm pinging you. So I received it, and I reply back. So you expect that because you're using TCP, but on my side, I'm using UDP because my UDP is a unidirectional. I just kind of send it, and I don't expect anything back. So it's a very good utility. It's one of the first things they need to try on a network. Is like, am I connected to the network? Can I ping myself? Can I ping a computer next to me? Can I ping the gateway? Then that's what I see if everything is working at the network card level on my computer. Now, the ping is also available if you're using IPv6. Of course, you usually ping an IP address, and on IPv6, it's kind of like lengthy to do that, but it is possible. So on Linux, you do ping 6 is the command. On Windows, you have to do ping space -6 followed by the IP address where you ping it, and that will work, to do the ping over IPv6. But it's the only difference: ping 6 or ping space -6 on Windows. And when I say Linux, also the Mac computers fall into the Linux computers, because Mac computers are now using a version of Linux. Then after ping, then you can use the IP config on any Windows machine that will give you the information on your IP configuration for your computer. Um, if you have Linux, it is if config for interface, if config. That will give you similar information, not put as well as Windows does, but it has also a lot of information there. But on my computer, when I did an ipconfig/all, it gives you a ton of information. It would read from top to bottom. First, my internal network, my internal domain is called Kenobi.internal. So that's my DNS suffix. So when I look for a printer, my C1664 printer, I don't have to put to print to D1664.kenobi.internal. I can just do .1664, and the computer will append that suffix, which is Kenobi internal. At Miami-Dade, all the computers have configured have the MDC.edu configured at this level. So if you do something, you try to ping or try to reach something, you don't have to put the whole full FUDN for internal traffic. Then the second line, the description, is my network card. So I happen to have an Intel Ethernet network, and it's the i219.lm, whatever. I think this would be a model number. And then look at the third line. That's my physical address. So ipconfig gives me my MAC address. That's my unique number, which starts the first half is the manufacturer. So most likely, if I query that, the 5098884C, that will return back that it is an Intel a network card. And my unique number is 5964F7. DHCP enable. Okay, so that means my computer was DHCP enabled, not manually configured. So the auto configuration enable, yes, it is auto configured. My IPv4 address is 10.10.100.32. My subnet mask is, we'll get into that later, is 255.255.255.0. All DHCP requests, when you get an IP address, it have what is called a lease. So basically, you're leasing that IP address. At Miami-Dade, I think we have the lease time for computers is 3 days. It depends on the environment. It depends what you have. That changes. In my house, I guess, I don't know what I put, probably 15 days because it's from 12 to the 29. So it's more than that, probably a month, because they don't change that often, right? But let's say on the Wi-Fi, we have a lease time of 3 hours because we want you to leave that IP address if you're not going to come back. If you came to class, you took your class, and now you're going home, then that I don't want that lease to stay there reserved for you for a week if you're not going to come back until the following week. So addresses are reusable, so you want to make sure that they get released. So that's why you have when you obtain it and when it expires. Then the next line is my default gateway. So it's giving me what's my router. My router is 10.10.100.1. My DHCP server is also 10.10.100.1. So that means that gateway is also the one acting as a DHCP server. And look at this. My DNS is not my default router. It's not my DHCP server. It's a different machine that is sitting on 10.10.100.10. That's my DNS server. So whenever I want to get a DNS resolution, my computer will go to 10.10.100.10. Case in point, I have only one DNS server at home, so it points only to that. If I have more than one, you can have a primary and secondary and tertiary too. So it will show there. Miami-Dade will show two, primary and secondary. But in my case, I have only one. The next line is NetBIOS over TCP. Yeah, it's enabled. NetBIOS allows computers, only Windows machines, to be able to talk over NetBIOS and share printers and share files and shit like that. So I have share things internal. So I have that enabled. And then my suffix, again, the search list. Also, if I'm looking for anything for DNS, it will try to append that Kenobi that internal just to see if it's something internal. But that's all that ipconfig /all would give me. It's a lot of information for troubleshooting. This is really important because you can see who's your gateway is, who your DNS service is, my DHCP server. I might be pointing to the wrong DHCP server. Someone might put a device that's acting as a DHCP server and getting the wrong IP addresses that doesn't have the information that network requires. So I would be able to troubleshoot that through here with just a simple command, ipconfig. This is the example from the book. And see now this one has a 802.11 USB wireless LAN card. Look at this one. The MAC address is still a 48-bit hexadecimal number. So the first four will identify who makes that wireless card, and then the first three, and then the last three, it will be the identifier for your card. This one is at 192.168.2.137. If you see the IPv6 is getting the FE80, so that's a link local IP address, right? On IPv6. So this is dual stack, right? Not like my home computer that has only IPv4. This is dual stack. There's your lease from Thursday, November 12th. The expiration day is Friday. Also, so on the 13th. So that's like about, it's not even 24 hours because the lease started at 8:51 p.m. It expires at 3:30 p.m. a.m. on the following day. So it's less than 24 hours. Anyway, so your default gateway is a 2.1, your DHCP server is 2.1. DHCP ID is a number there. That is something we declare UID is something different. And then your DNS service here, you got two DNS servers, 1.1.1.1 and 1.0.0.1. So now you got primary and secondary DNS servers. It will do the request in that order. It will always go to the primary. If that fails to reply, then it will go to the secondary. But it's not a round robin that will go, sometimes to one, sometimes to the other. No, it's primary and secondary. Okay, NetBIOS, yeah, is enabled on that computer too. Now, the author is trying to be a little smart here and throw some Linux tools for you. The IP utility is how you manage IP addresses on Unix and Linux systems, not on all the version of Unix and Linux, because it varies from one flavor of Linux to another flavor of Linux. It depends on what you're using. But the IP command, it's supposed to be the latest that is on Ubuntu, on Fedora, and other flavors of Linux that use IP. If not, you can use the IF config. There used to be an ETH tool like Ethernet, ETH tool, all one word together. There used to be another utility. If you don't have it on Linux, you can also install it, and also gives you a better handling on your IP address and information from the console. Not from the GUI, but from the console. If you want to use the GUI, yeah, you can also do a shell and do ifconfig, and you open the utility. But it varies on Linux. Varies. It's not like, of course, Microsoft is just one operating system and they maintain their settings. But on Linux, there's so many different flavors, including the Mac OS, that it varies from one version to another. For a lot of the stuff on Linux, you have to use the sudo command or the super user do. That gives you privileges to request some information and to elevate yourself and make changes to your IP configuration. For Linux, yeah, if you had the password, because it will ask you for the super user password. So if you need to make a change on the operating system, you have to use sudo. They don't recommend for you to log in as a root. Well, the root is the main God administrator for a Linux system, but they don't recommend to use that. So you use the sudo command. So here, for example, if you're on a Linux machine and you want to change your host name, you can say, just do host name. It'll show you host name. If you want to see the full FQDN, you do hostname-a. That will give you, that is mshome.net. If you want the IP address, so hostname-i, it will give you the IP address associated with that host name. But if you want to change it, you have to do the sudo, the sudo super user do host name. You see, it would ask you for the password. That has to be a administrative password, and then it would change the name. But that's on Linux. Another tool that's really, really important to use is NSLookup. NSLookup will actually do the query to a DNS server. You can do it straight on the line instead NSLookup space and the fully qualified domain name, and it will reply back with the IP address. Or you can just run NSLookup, open the utility, and from there it will tell you which server you're pointing to, and then you put www.wc.edu, and it will reply back with the IP address. Now, if it doesn't reply with an IP address, because you cannot reach www.mdc.edu, and NSLOOKUP cannot give you an answer, is because something wrong with your DNS configuration, your computer, and you cannot reach anything anywhere that can give you an answer for what's the resolution for that. If you want to do a reverse lookup, again, NSLOOKUP space and the IP address. Or if you open the utility, I'll show that in class though. I'll show that in class just to make sure that you understand that. But on your computers, you open a command line, CMD on your search bar. Open the command prompt interface on Windows, and then you can run this example just to see how it works. You can do NSLOOKUP www.google.com, and then with IP address, whatever IP address you get, then do it again with the NSLOOKUP space with that IP address and see what you get, right? Um, the NSLOOKUP, it comes in the two modes, interactive or non-interactive, where you can do multiple servers, but most likely it will be interactive. That's the default. Okay. Once you're done with utility, just type exit if you're in utility. If you do it from the command line, then it will just give you a reply and you go back to the command line. But it is important. NSLOOKUP has also other switches that you can use. That when you type NSLOOKUP, and if you do space slash question mark, they will give you all the different options that you can do with NSLOOKUP. So if you're on a Linux or a Mac OS machine, you don't have the NSLOOKUP utility, but you have dig. Dig is the domain information grouper. That it's also similar to NSLOOKUP, but this one gives you a little more information than NSLOOKUP. So it's it's just different. But you can use that to get the same kind of result that you get from NSLOOKUP. You can use dig on Windows, but in order to do that, you have to install Bind. Remember, the Bind is the most popular DNS server in the IT world. So you can install Bind on your computer, so you can get on Windows, so you can get that Bind utility, make it run on Windows machine. I mean, I guess if you're like a hardcore IT administrator and you might want to have that on Windows. Actually, if you think about it, if you're really hardcore, you might have a Linux machine next to you, your Windows and a Linux. So you can just go to a Linux machine and do dig if you want to on that other machine. If you're really hardcore, you might have a virtual machine running with both, with Windows and Linux, so you can run on both. It can be so complicated, but dig is a good utility. And then you can have an IP scanner. We saw that in the previous chapter, that you can get information on all the devices connected to your network. Now, the last few slides is on common issues on computers. The time is so important on your computers. Usually, when you set up a computer that is new, they might set you up in the wrong time zone, and I think it defaults to like California or something like that. So I always get confused when I set up a new computer and it's late at night, and I look at the time and it says like 9:30. I'm like, oh, it's early. When I realize it's not 9:30, it's actually 12:30. So you have to make sure that you have the right time. On Windows, you can do the W32TM and do /query/source, and that will give you the source of the time and see the time that they're using your computer. But there's a lot of communication, especially when you're trying to do a secure communication to anything now with HTTPS, anything SSH, anything using SSL encryption. SSL is a secure socket layer encryption. Needs to have the right time. If you don't have the right time, it's like asking another server with the correct time, hey, I need this information, which is encrypted information and it's private information, your bank. So you go to your bank and your bank is like, okay, it's 10 o'clock right now, but your request says 8 p.m. So that request must be old, and for some reason it took 2 hours to get to me. So I'm going to drop it. I'm going to ignore it because I'm not going to communicate with you because it's a time warp. You're coming from a way different time. And imagine the other way around, that your service is at 8 p.m. and your request comes from 10 p.m. And the server is also going to look at that, match the time. It goes, something is not really right. on this communication here. So let me just drop it. If you're working with databases, it's really, really important that you have the correct time. So computers have a way to synchronize. So most likely what you want to do if you have an enterprise network is to set up an internal time server and then have all your computers go to that one to get your time. Windows wants to be the time server. So if you have a domain controller, Windows wants to be the time server for all of those workstations to make sure all the communication, all the Kerberos, all the Kerberos is a way to grant the tickets to give you access to certain files, information on your network. So to use Kerberos, Kerberos relies a lot on that timing. So that's why they want your Windows server to be your time server. So even though your Windows server is wrong, then all the computers are going to be wrong. But then as per the server perspective, everybody's on the same page, everybody's at the same time. So that works for them. DHCP issues, if you have DHCP server issues, you may get duplicate IP addresses, scopes that run out, that they don't have enough IP addresses, or my Wi-Fi, and I said the college Wi-Fi. The college Wi-Fi, if I have 1,000 IPs available, right, and I expect to have 500 students every day coming in. If I give you a 1 week lease, meaning that you can have that IP address for you for a week, what happens by Tuesday, Wednesday, Thursday, Friday? A lot of IPs are going to be held up for all those clients that came. Even if you don't come back for classes, you just came on Monday, you don't come back on the next Monday. Your class is only on Mondays, right? You come on Monday, you don't have to come back on the following Monday if you're not taking the class at the Kendall campus. So those IPs will be held up for you. So what you want is to have that lease time to be shorter. So when you go away, and after a few hours, then I'll release that one and somebody else can use it. Another thing with the DHCP is that you might have also a conflicting DHCP server. Like I said, I know that I have a 147.70 IP addresses inside the college, and somebody calls, he goes, I can't connect to the network. I said, open a window. Could you please do IP config for me? And they do IP config. It goes, what's your IP address? Oh, 192.168.175. I'm like, oops, I don't have any DHCP server in the college that we don't have anything that it hands out 192.168 that something IP addresses. So somebody connected something on the network and is handing out those IP addresses. Some of the Linux servers, when you install it by default, they used to have the DHCP server enabled by default, and they want to be the server. So when they connect that and they install it, the person doing that is not aware of that, it will put another DHCP server, and the DHCP server works in the faster response. So if I'm in building 8 and someone bring a server there, and there's a DHCP server there on building 8, that is not managed by the college. When you do a DHCP request, it will send a broadcast to everywhere, right? So it needs to reach the ones here at the Kendall data center. So by the time the Kendall data center replies, chances are, and it will, that the one that was set there at the building 8 at somewhere on another floor, it will reply quicker than mine that's coming from the data center. So your computer will get that IP address, even though the other one it came too late, a few milliseconds later. So just by having that rogue DHCP server closer to you, you will get the wrong IP address. And it happened a few times inside the college through the past years. So we see it over and over. So that's why we always ask, could you open your command line and do IP config and tell me what you see and read me or send me a screenshot so I can, look troubleshoot it through that. And that's when you see some DHCP problems. So that leads to, common issues like the incorrect IP address because you didn't get it from me for my servers. Duplicates when there was a lease that was not expired and the server kind of provides it again, or your computer held it for too long, and when you came back and you connected, then you got a duplicate. When you have a duplicate, usually one of the two machines will back out a little bit and they'll try to connect again. I don't know now, but in the old days, what Windows will do is like back out for like a minute and try to connect again, and if you will see there's still a conflict, it will back out for 2 minutes. And they'll keep doing that double the times to go 1 minute, 2 minutes, 4 minutes, 8 minutes, 16 minutes, and like that until they get like an hour, and then they'll come back like that. Subnet mask. Subnet mask we'll see later on when we get into IP addressing how the subnet mask divides the network in different areas, different subnets, different groups of IPs. And so if you don't have the right subnet mask, you might be appear to be part of another network that you don't belong to. The gateway, if you had the wrong gateway, it's like pointing to the wrong door. It's a room, and it has the front door to come in and out, but in the back there's a door to a closet, and then you get point to that door, not the main door. Of course, you go to the closet, you're not going to go anywhere. So you have the wrong gateway, or God forbid you're pointing to another computer as a gateway. That computer has no capabilities, and he's not aware, or he's trying, someone's trying to use it as a gateway. So he's not capable of routing any traffic. So he's just going to ignore that traffic. DNS issues, incorrect DNS, you're pointing to the wrong DNS server. Or the DNS itself, you cannot reach it, or something wrong with that DNS. It doesn't have the right configuration for the authoritative server, so you cannot get information to get also to the your top level domains, anything like that. So you looked at. When a computer cannot get into the network, then check your TCP/IP configuration settings. Make sure that IPv4 is enabled, that it's enabled on the right network card, that you don't have multiple network cards on the same network. It happens a lot now that computers, laptops, people come in, professors or students, and connect to a wire, but the Wi-Fi still turn on. So your computer will try to connect to the Wi-Fi, but then also get an IP address through your wire. So you actually have two IP addresses for the same network. So for some things, it will go one way, for things will go the other way, and that will create some latency problems. Sometimes some things will go seems faster, some other will break. So it creates a problem. When it comes to something like that, you disable one of them. What do you want to use? You want to use the Wi-Fi? You want to use the wire, but don't use both at the same time. VPN. The VPN gets totally confused if you have the two enabled on the same enterprise network, right? If a computer doesn't get the right IP address, it will default to a kind of like the FE80 from the IPv6. It's called the API-PA. API-PA is an IP address that you will see on computers is 169.254, that's something, and it will come up with an IP address. And when you see that, it's because your computer did not get an IP address and it self-assigned one. But that's a Windows self-assigned, Windows only self-assigned IP address that it would actually work on an environment where there's no DHCP server and they all self-assign an IP address, and by luck you don't get a duplicate because it's like 65,000 permutations that you can have with an IP address. So they will be able to work and communicate within each other if you get one of those IP addresses. But once you see that your IP address is 169.254 dot something something on IPv4, that means that it will self-assign. FE80 is a self-assign for IPv6. All right, and that's it for this module 3 or chapter 3. So we went over the MAC addresses, the TCP/IP settings for IP addresses and the IPv6. We spoke about DNS, some of the port numbers, DNS and how it works, how the resolution works, and how it's configured, and some utilities like NSLookup and things like that, and your troubleshooting. But remember, at least those 3 utilities on Windows, your ping, ipconfig, and NSLookup. I used all those 3 daily. If you are on a Mac OS or Linux environment, then ping is there. Then you use ifconfig or IP, and also for the NSLookup, you'll use the dig command. Dig would actually give you all these more information that NSLookup can give you, but this utility is available on both systems. Okay. Well, thank you very much. I know this has been a long video, but try to dig into it as much as I can. So thank you very much.